example 6b, we've got tangent of 2 arcsine 2/5. What I want you to realize is this arcsine, this inverse trig function, is an angle. So if you think of that as angle A, then maybe it's a little bit more obvious what's going to happen. We have tangent of 2A, or tangent of 2 times the angle. It's a double angle identity. So hopefully that makes you want to look over at the formulas, look them up on the formula sheet or up on the board. Tangent 2A is equal to 2 tangent A over 1 minus tangent squared A. So we're going to utilize that identity, but first we're going to draw a picture of the angle. Okay, this is an angle. And so we look at inverse sine, and we know the range of inverse sine is from negative pi over 2 to positive pi over 2. But that means that it's defined in quadrants 1 and 4. So we're either going to have a picture of an angle in quadrant 1 or a picture of an angle in quadrant 4. And so you should notice that this is a positive fraction. That the 2/5 is a positive ratio. And what that's going to do is that's going to tell me that I'm in the positive realm. We're in quadrant 1, not in quadrant 4. And so what I ought to be able to do is draw a picture of that angle in quadrant 1. So let's do that. We're going to have an angle, and I'm going to label it angle A in quadrant 1. And we see the sine ratio here. The sine ratio is 2/5. So we know that sine ratio is y over r. And that gives me two of my sides of my triangle, the y side and the r side, 2 and 5. And so we use Pythagorean theorem like we always do. X squared plus 2 squared equals 5 squared. X squared plus 4 equals 25. Maybe you can do this in your head. But you're getting x equals plus or minus square root of 21. But since we're in the first quadrant, we know that's going to be the positive version. Square root of 21 right there for that missing side. Once we have all three sides of that triangle, you should be able to give me any of the 6 trig ratios that I asked for. We know an awful lot about angle A at this point. But when we look at our formula, we want the tangent ratio. And so we know the tangent ratio is y over x. And so you look at your y over x, it's going to be 2 over square root of 21. Tangent A is 2 over square root of 21. So we've got this expression, and the rest is just going to be algebra we clean up. Okay, so cleaning up our fraction a bit, 2 times 2 over square root of 21 is going to be 4 over square root of 21. And then on the bottom, we've got to square that quantity, but that's actually good because that's going to make the square root go away. We'll have 1 minus 2 over 21. At which point we're subtracting fractions, and we see this all the time. If we're subtracting fractions or adding fractions, we need a common denominator. So let's call that 1. Let's call that 21 over 21. Oh, I have a mistake. I forgot to square that 2. That's actually going to be 4 over 21. When I square that 2 over square root of 21, that's 4 over 21. Okay, but I get a common denominator. I'm going to have 21 over 21, and that's going to equal 4 over square root of 21, all over 21 minus 4 is 17 over 21. Every time I get a problem where I divide fractions, I'm going to multiply by the reciprocal. So if I multiply the reciprocal, I'm going to have 4 times 21 over 17 square root of 21. And you can multiply 4 times 21 and get 84 if you want, but I know what's going to happen when I rationalize this denominator, and so I'm leaving it. You rationalize the denominator in the usual way, multiply the square root of 21 over square root of 21, and that turns into 21. And so I have a situation where it looks like I can cancel those 21. 21 cancels the 21, and I'm looking at 4 times the square root of 21 over 17. I think the hardest part about this is just cleaning up all the algebra. We're doing fractions, we combine like terms, or get a common denominator, we multiply by the reciprocal, we rationalize the denominator. We do the same kind of algebra stuff